This is the first video for atomic structure and periodic trends, which is chapters 6 and 7 in your textbook. And unlike many of the previous chapters, there's not a lot of calculations, and even with a few of these first concepts, the first videos, there's not a lot that you need to be able to explain. It's just kind of the groundwork that gets us to the point of understanding why the periodic table is arranged the way that it is, what we can know about the periodic table from its arrangement, and gets us to the place where we can start to predict and understand properties of elements and bonding, which is what we'll get to in the next unit. So in understanding atomic structure, we remember, hopefully, that the idea started over 2,000 years ago, but it wasn't until about 1900 where the structure was really starting to be explored. And it was in the early 1900s that they started to know more and more about the electron, which is really most of our focus here about atomic structure. So these are some highlights of the how we got to where we are, but it was really some other people, Planck, Einstein, Heisenberg, de Broglie, Schrodinger, that got us to the point of really understanding the role of the electron. So the key of Max Planck's work was relating the way that elements or atoms or basically any substance was gaining and losing energy and trying to understand how much energy they could gain or lose. And out of his work came an equation, E equals h nu, and this equation is on the periodic table. And when I said it, I didn't say the n. The n is an important part, but it's really just saying that once we know the amount of energy gained or lost, we could double that amount of energy or triple it. But what came out of this was an understanding that the energy is actually related to frequency. So frequency is what that V looking thing, or a nu, stands for in this case. So we can say when the frequency is large, we absorb a lot of energy. When the frequency is small, we're absorbing less energy. But there's only certain amounts of energy that can be absorbed or released. And this equation below this, C equals lambda nu, relates to light. So at this point there wasn't a big connection between light and matter and energy, but it's something that we'll see later. So this nu, we do know, is related to the speed of light or to velocity in general by the wavelength of the energy, or by the wavelength of the radiation that's being emitted. So we can make a connection between all of those things. We've got a couple constants here, and this equation are both given on the periodic table. The value for H, the value for C are both given on the periodic table. You may have to do some simple calculations with this, but one of the most important things to know out of this is that energy, when that goes up, frequency goes up. So really energy is proportional to frequency, whereas with wavelength, when that goes up, it's because our frequency went down, so our wavelength is proportional to the inverse of our frequency. Definitely a possibility calculations could come up, but much more likely that it talks about the higher the frequency, what do we know about the energy? Or the higher the wavelength, what do we know about the frequency? Or we'll see in a second the connection of those two things. And this is just a real quick overview, and I've already said that, of these topics, trying to get to the highlights, but you need to read through this to understand it, and definitely dive into your book to really get the details of it. But building on the work of Planck was Einstein, or building on all of this, or maybe not so much building on it as making some connections to things that weren't totally understood before. Once people saw that relationship there and saw that energy was related to frequency, there started to be a lot of things that fell into place where there was other relationships that could then be explained. And Einstein was able to explain the photoelectric effect, or the idea that when we shine light on a metal, sometimes electrons can be ejected. and there was some kind of inconsistencies or some things that weren't happening the way they were predicted. You could have really, really, really bright light shining on it for a very, very long time and have no electrons come out. Or you could have a different color of light shine on it very dimly for just a little amount of time and electrons would be ejected. The difference there was the frequency of the light. So we said frequency relates to wavelength, frequency relates to energy. So that connection, that certain colors of light that have certain frequencies and wavelengths have enough energy to move those electrons and to eject them from the metal. So we're able to put this equation together in a couple different ways. Energy related to h nu, energy related to hc over lambda, and connect it even with Einstein's famous E equals mc squared to see that there was relationships now between energy, frequency, wavelength, and mass. And all of this established the idea that light may actually act two different ways. It may act as little particles that were called photons, or it may act as waves, have frequency, have wavelength. So we've got these two opposing things happening that was explaining light and things that they knew, or yeah, I guess we knew about light in a totally new way. The next major jump from this was, okay, if light isn't just going to be acting like a wave, if it's going to be acting like a particle, is it possible for other particles or other things to act in this way and have a dual nature? And that's where de Broglie came in and came up with the idea that if light acts as a wave, so if and a particle, so if something that's a wave acts like a particle, let's see if our particles can act as waves, and came up with or rearranged or solved for what would be the de Broglie equation. This is not given on the periodic table. It's very unlikely you'd have to do a calculation, but it is possible you would have to know the relationships that we're going to discuss right here. The idea that massive objects have small wavelengths and that things with very, very, very small masses, once we get tiny, like we start talking about things like electrons, we actually get a wavelength that is measurable. So out of this came this statement. We know that energy is really a form of matter, and all matter shows the same type of particles. So that means all matter exhibits the properties of a particle and a wave. This is where a big leap forward came in understanding or building a model of what the electron was doing. It was fairly simple to establish and understand the idea of that there was a nucleus and what was there, but to understand the electrons was much more complex. So there is a problem here using the de Broglie equation. Like I said, it's not one you're necessarily going to have to solve for, and I'm not going to spend tons of time doing the math here, but it is lambda equals h, and h is Planck's constant. It's still 6.626 times 10 to the negative 34th, and that would be joule seconds as our units. And if you wanted to know your wavelength of anything, it would just be over the mass of it in kilograms times the velocity in meters per second. So we have two things here, an electron, a tiny mass, 9 times 10 to the negative 31st. When we solve for lambda on that, it gives us our speed here, traveling pretty fast, traveling near, not at, but kind of in the ballpark of the speed of light. It has a wavelength that is 0.0000000007. I think I counted that out right. 7 times 10 to the negative 11th. But when we have something bigger, a ball, a tenth of a kilogram, much slower, 35 meters per second, its wavelength is impossibly small. So when we think about this, these electrons actually have a wavelength that could be observed, and they could actually be something we treat as a wave, whereas a ball, yes, we can calculate its wavelength, but it's so small it's unlikely or not useful for us to think of it in terms of a wave. In the traditional discussion of atomic structure, you normally talk Thomson, you talk Rutherford, and then the next big stop is Bohr. So just really quick, we filled in a few of the gaps there without much detail. Definitely know there's a lot more, and you can read a lot more. Once again, chapter 6 in your book. But what Bohr was doing was building on those same ideas, recognizing and figuring out that there was a relationship with energy that had something to do with the atoms. And the Bohr model did a great thing, was it gave a specific connection of the energy that everyone's been observing with the structure of the atom, the electron. So what he was looking at, and you can read this, but it had to do with, right here, I'm going to focus just on this, because this is definitely some data or something you could be asked to look at or explain, was how different elements, instead of giving off a full spectrum of light, when that element, and this one's hydrogen, is heated up, it only gives off light of a certain color. So instead of giving off all the different possible energies, there was only certain frequencies it gave off. Those frequencies connect with an energy, and the question was, why did hydrogen, for example, give off this energy, this energy, this energy, this energy, but nothing in between? And why was helium different? And why was every single element different? And what he was able to do was understand that this had to do something with the electrons and come up with the idea of energy levels or energy states, and this conclusion: the electron in a hydrogen atom can only occupy certain energy states. Very important idea. And when you think of an atom, many people think of that Bohr model with 2 electrons in the first ring and 8 in the second ring and 8 in the third ring, because so much of what he did connects still with what we know. So I'm going to kind of brush over a lot of this stuff. You definitely need to read it. It kind of fills in a few gaps. It reminds you of what you know about the Bohr model. It gives you an equation here, and we'll do a calculation or two with this. But the reason we didn't stop, and I'm jumping down here, with the Bohr model, yes, energy levels are great. Yes, energy is related to where the electrons are. They can go up, they can go down, they can absorb, they can emit. Very important things to know. Connecting to quantization here. We're still using that quantum term, but the problems with the Bohr model, and we use not the Bohr model, with Bohr's complete theory, we can still use a Bohr model, is that it only works for elements with 1 electron. So really that's only hydrogen, or if we ionized helium or we ionized lithium by losing 2 electrons, it would work. Really, if you had lead with 81 of its electrons lost, so it's a Pb plus 81, it would work for that, but it doesn't work for anything even as simple as helium with 2 electrons. The other problem is it was all based upon assumption that electron was orbiting the nucleus in a fixed path, or at least a fixed energy state. But there was some observations that had to be ignored, because when something orbits, there's energy changes associated with it. And what Bohr kind of did was he kind of cheated to make it work. Everything else made so much sense. Numbers that existed and observations that existed that could never be explained before could be explained by thinking about energy levels and energy required to move up and energy released when moving down, that those other things kind of were thought of as secondary, not totally ignored, and that's why the Bohr model wasn't the be-all end-all, but put to the side with the strengths of the model coming to the front of this. So we're going to do just really quick look at this equation and look at it in terms of some calculations. It's very unlikely you'd have to do these calculations, but understanding these calculations means you understand the Bohr model and what it says. And then we'll move on with the next video to the quantum mechanical model, to a little bit closer to a more complete model of the atom. As we do these two calculations, we're going to kind of conceptually talk about some stuff. So the first thing we have with this, we've got energy. That's the key. That was the connection to all of these other things. There is a constant. This constant accounts for a lot of pieces here. But one of the interesting things about Bohr is that he had all this data, he had an idea, but it wasn't until even some other people started to explain some ideas and take some data and publish some of their ideas that he was able to complete his model. So taking our constant, we just need to put some numbers in here to make sense of this, to do our calculations. So the two variables in this equation are z and n. And z is the nuclear charge. It's very easy for hydrogen, so it's 1 squared. N is which energy level it's on. So you can be at the lowest energy level 1, you can go up to 2, 3, 4, etc. So we are exciting an electron from level 1 to level 2, so we're going to end at level 2. And I could do this number and then subtract the other number, but since the constant is the same for both, what I'm going to do is right here, what I have just written, and then I'm going to undo that, that would be the energy associated with the electron on energy level 2. And then I could do the energy associated with the electron on energy level 1 and find the difference between them. But like I said, the constant is the same for both of them. So I'm just going to do minus, we've got this, over 1 squared. So the 1 on top is the same because we have a hydrogen atom with a charge of positive 1. The number on the bottom is different because we're talking about two different energy levels. We are moving up in energy this time, but we're going to do our final minus our initial. The negative sign is related to the fact the closer it is to the nucleus, the more stable it is, compared to an electron by itself being very unstable. But if you do the math on this, you basically come up with, let's see, 1 over 1 is 1, so we're just subtracting 1. This is a fourth minus 1 is this, a fourth minus 1 is negative 3/4 times this negative number gives us our positive value that you would get over here. So we've moved up in energy levels, we had to put in energy. If we were going from level 2 down to level 1, we would swap these two. Our energy then would be given off, and we would say our delta E is negative, exothermic. This is an endothermic process. The second one's the exact same idea. Calculate the energy required to remove an electron from a hydrogen atom in its ground state. So a reminder that ground state means that we are starting at, so our initial value here is the same. We're at n equals 1, or the lowest possible energy level. So for removing it, that means we're going to the highest possible energy level. And not just the highest level on the periodic table that's been discovered so far, which would be level 7. We're going beyond that, or we're removing it. So really, this is infinity. And it seems silly to square infinity because infinity squared doesn't mean anything different than infinity. But this right here is basically 1 over a huge number is equal to 0. So we have 0 minus 1. So we're taking it from where it is based on the amount of energy, the stability it has by being a part of the nucleus, and totally removing it. Or really, 0 minus 1 here, this is negative 1, so this is canceling out. Basically, and this is a 1. So right here, and this is kind of all sloppy, you see that that value is equal to that. By being in the atom, that electron has that much more stability than if it was totally out on its own. 1 electron in 1 hydrogen atom. So this used to be a calculation that was pretty common manipulating these numbers. So if you look back in some old AP questions, don't be surprised if you see some calculations with this. But really now I would expect more of a conceptual understanding of how energy relates to moving to a higher energy level or a lower energy level or being removed from the atom. Which state's more stable? How does that connect with the Bohr model? How is that different maybe than Rutherford's model? How is it different than the quantum mechanical model, which we'll get into the next video? So definitely don't just jump around like I did. Read the things between there. It's not going to take long to do this. Make sure that you understand conceptually in addition to mathematically. And this would maybe be the one section that's worth skimming your book and kind of filling in those details a little bit more, kind of a lot of this chapter 6 stuff.